everyone. Thank you for coming to our session on the change block tracking. My name is Xing. I work for VMware by Broadcom. I'm also a co-chair of Kubernetes 6 storage and the data protection working group.
Rob, can you help us with that? No. All right, we'll talk over them. Hi, I'm Mark Lavi. I'm the open source product manager at Veeam Kasten, and I'm joined by one of my colleagues. He'll tell us about the other colleague just now.
Hi, I'm Carl Braganza. I'm one of the technical staff at Veeam. I'm one of the co-authors of the CBT KEP in Kubernetes. Prasad and Ivan, two others. Prasad was going to join us today, but unfortunately couldn't make it. I'm also one of the authors of the CSI edition for this KEP. Right.
All right, I'll just try to talk over him. All right, today we're going to go over change block tracking, its motivation, history, architecture, implementation with respect to Kubernetes. We'll demonstrate a workflow and then leave you with resources and how to get involved. We want you to adopt it, and we'll answer any Q&A at the end. With that, let's get started. So change block tracking is what everybody expects when it comes to Kubernetes and cloud-native storage and applications. However, it is a lacking feature. When we compare to traditional storage, how do you do the difference between any two volume snapshots? Well, you need to take another full backup, but everybody else in traditional VMs and bare metal world already has this. So in order to come down on what we measure, RPO, RTO, for all backup and recovery and disaster recovery, we need to be able to get to change block tracking in order to make sure that if the difference between any two volume snapshots is nothing, well, I don't want to take a whole nother backup, a whole nother consumption of storage, network, compute, and memory. No, I want a zero delta, zero metadata pointers, etc., right? So that is what change block tracking brings, and we've brought this forward because everybody's coming to Kubernetes from the VM world right now. They want change block tracking because they expect it. And you needed to go to a proprietary vendor's driver in order to get change block tracking or explain why it doesn't work with CSI. We've changed that, and this is a critical unblocker for Kubernetes adoption. We created KEP 3314 to do this, and we have now completed implementation. So the history is that we started this well over 2 years ago at the Data Protection Working Group. The design has gone through 3 major iterations, and we've had lots of fun defending, improving, going backwards, improving again, and defending over 3 major revisions. And it's taken SIG storage, SIG auth, SIG architecture, the API reviewers, CSI reviewers, storage vendors, backup vendors, the community contributions. It takes a village, quite frankly, to get to this point. It's not been fun, but we've arrived, and we're very excited to have arrived with an implementation in the CSI specification, and now we're ready and finished with the implementation, finished with the end-to-end testing. This is now ready to ship with Kubernetes 1.3.3 alpha APIs. So we'll talk more about how to adopt it next. But that's where we are. So I'm going to hand over to Xing to explain our architecture and implementation.
Thanks, Mark. So to support CBT in Kubernetes and in CSI, we added a new snapshot metadata service in the CSI spec. We also added 2 new CSI RPCs. Get metadata allocated retrieves the metadata of the allocated blocks for a single snapshot. Get metadata delta retrieves the metadata for the change blocks of 2 snapshots for the same block volume. Now this feature supports block volume only. Support for file volume is out of scope for this design, but we can consider that in the future. To add CBT support in Kubernetes, we also introduced 2 Kubernetes snapshot metadata gRPC APIs, get metadata allocated and get metadata delta. The backup software will be calling this Kubernetes snapshot metadata APIs to retrieve snapshot metadata. This design is very different from other Kubernetes APIs we have designed so far in SIG storage. We did this way to avoid overloading the Kubernetes API server. In the worst case scenario, while every block is changed, we could potentially get 5 gigabytes of metadata per 1 terabytes of volume data. So that would definitely overwhelm the Kubernetes API server if we choose to use the custom resource to store the metadata. We implemented this Kubernetes snapshot metadata in the snapshot metadata sidecar, a gRPC service. This gRPC service calls CSI driver to retrieve the snapshot metadata. We do have a new snapshot metadata service CRD. It contains information on how to connect to the gRPC service. A CSI driver creates this CR, advertise that the gRPC service is deployed together with the CSI driver. And the backup software will be fetching the CR and tries to connect to the snapshot metadata sidecar, the gRPC service. Now let me talk about the backup approach with volume snapshots. In a typical backup, a backup software creates a volume snapshot from a PVC that is part of an application it tries to back up. Then it creates a PVC from that volume snapshot, launches a data mover pod, and attaches the PVC to the pod. And then the data mover pod will try to copy data to the backup storage repository. The backup software manages the lifecycle of the volume snapshots. A persistent volume can be a volume mode that is either block or file system that specifies how this volume will be consumed by container. It's either a formatted file system or a block device. Usually, it is more efficient to consume the volume through the raw block mode compared to through the file system. In this talk, we're going to be focusing on the block mode use case. So in this talk, we are going to focus on the snapshot metadata access optimization. We are going to talk about how this works currently without this feature. Without CBT, a backup software will have to call vendor-specific APIs to retrieve snapshot metadata. For a full backup, it needs to query the allocated blocks. For incremental backup, it needs to query the change blocks. So that is highly inefficient. With this feature, we are going to have Kubernetes snapshot metadata API. It provides a vendor-agnostic way to retrieve the snapshot metadata. So now the backup software can call this common API to query allocated or changed blocks. This is an optional CSI feature, so a CSI driver can implement this. It is an alpha feature, as mentioned earlier. Now let me hand it over to Carl, who will talk about the CSI driver deployment.
Thanks, Xing. So as Xing introduced this topic, right, there are two APIs, really. There are two gRPC APIs. There's the CSI API, which actually the CSI driver will implement. And that API is the one that actually provides the raw data. But Kubernetes applications don't talk the right language for a CSI driver. Also, the CSI API has one client. It's not designed for multiple clients. The Kubernetes domain clients are not the CSI driver clients. Instead, we have a sidecar which intercepts and protects the CSI driver from Kubernetes clients. It performs all the authorization, RBAC checks, and name translation required to take Kubernetes objects into the CSI namespace. So a CSI driver will deploy this sidecar over a Unix socket, the same Unix socket they use today, right, for the other sidecars which they deploy. The sidecar will implement the Kubernetes version of this API. It's almost identical to the CSI version, with the exception that it takes an authorization token, security token, and it takes names of Kubernetes objects. So this is an optional feature. Not every CSI driver will have it, right? And so how does an application figure out that this exists? So when the CSI driver installs this, they are required to create a CR named for the CSI driver. That CR contains the endpoint information of the Kubernetes service, namely the sidecar. Typically, a CSI driver will install a service object, and the service object will have information, the namespace of the CSI driver. Other things can be used to create a DNS name. The CR is also required to have a CA certificate and an audience string. This is for mutual authentication, right, as you'll see in the next few slides, and so security authentication. So I'm going to go over the workflow of a backup application. So the first thing a backup application would do would be to determine whether this feature is available. And it's a very simple thing. It just looks for the CR based on the name of the CSI driver. Of course, it gets that name of the CSI driver from its either the PV or the volume snapshot, right, or any of these objects. Once that's done, the backup application has to ask the Kubernetes API for an auth token. And this auth token has to have the audience string specified from the CR. And we'll get to the reasons in the next few slides. Now, at this point, with the data from the CR, we have the endpoint, right? And we have the audience string. So the backup application is now in a position to make a call to the sidecar using the Kubernetes snapshot metadata gRPC API. This is not going to the Kubernetes API server anymore. At this point, the gRPC call is one-way authentication, right? The backup application trusts that the sidecar is what it is. But the sidecar knows nothing about the backup application. However, in every one of these RPC calls is the Kubernetes authentication string we've obtained from the previous step. So the first thing the sidecar does is contact the Kubernetes API to validate that authentication string. So now we've reached mutual authentication. At this point, the snapshot sidecar will also look up the names of the snapshots which are part of the API calls and validate access through subject access review APIs, and also pull in the metadata of those volumes so that it can translate the call into the language of the CSI driver, namely pull out the CSI IDs, the snapshot IDs and the volume IDs. At this point, it proxies the call through the CSI snapshot metadata gRPC call to the CSI driver. CSI driver, you notice, has nothing to do with the Kubernetes side of things. It's totally shielded from this. CSI driver does its things, and data is streamed back through the same gRPC call, totally bypassing the API server. So the only actual contact with the API server is to read the CR, do the subject access review, and auth calls. All right. To make this work, right, you have to have adequate security policy. I'm not going to go into much detail in this slide. There's a lot of stuff there. But the most important things to note is that use of the token request, token review, and subject access reviews APIs, which are not normally touched by backup software. So the CSI driver has to have permissions for subject access review and token review to validate and check permissions. And the backup application, when it installs itself, must make sure that it has adequate permission to perform a token review, a token request. Most of the other permissions exist just because they're backup applications and CSI drivers. So the work we've done, which includes developing the sidecar, is all in the Kubernetes CSI external snapshot metadata repository. So a lot of stuff there. It's got the gRPC protobuf specifications, stubs, and mocks for the Kubernetes snapshot metadata API. The CSI metadata, CSI gRPC spec is in the CSI repo, right? You can reference it from this repo, but most application developers won't need that. The sidecar container logic is there, and as well as the CRD for this for the snapshot metadata CRD. We have utility packages to help you as an if you are an application developer, right? Help you write and use this stuff. We don't, it's complicated to deal with so many different with this workflow. But we have an iterator package that does all the steps for you. If you're using Go. If you're not using Go, then the protobufs and all the supporting stuff are available for whatever language you want. And there are other additional resources to support CSI driver development. There are tools we've added there, which are used by CSI developers. There are other resources accessible. The Kubernetes CSI developer documentation has been updated to include this feature and talk about the change block tracking feature. It also has links to pretty much everything we're going through in the slides. Okay, we'll go through a demonstration. All right. Sorry, where are we? Yep. I'll just talk a little bit about what I'm going to demonstrate, and then we'll go through a video to show this. So it's a little bit of an eye chart, right? But we're going to use the CSI host path driver. The CSI host path driver is not a quote-unquote product-ready driver. It's a development test tool, which CSI developers use to run unit tests and other things. This was the first vehicle we used to implement this spec and test it out. So the CSI host path driver has a mode of deployment, right, where you can attach the sidecar, the snapshot metadata sidecar we developed. It has, because it's used for lots of testing, this driver only with block volume mode supports this feature. But it's a minor issue. Real CSI drivers will support this feature for volume or file system mode. So we have a very simple app which is going to create a PVC and mount it in block mode. We will add data to that PVC and take a snapshot, right? Then we'll use this pod over here, create an application called the CSI client, which is one of the tools we provide in the snapshot repo. External snapshot metadata repo. And that tool provides the mechanism to actually use this iterator and will work on things. It's in a pod by itself because typically backup applications will be in different namespaces, right, to work. After we do that, we look at the allocated blocks. Then we'll go back to the app and cause a change. Add some more blocks to the volume and then snapshot it again. And then once again use the tool to see the change blocks. Okay. Let me get to the. All right. Okay. I will move this around to hasten this. We've seen this already, so okay. So the first thing we're going to do is create this application. So it's just a simple app. So we use a CSI host path storage class. It's part of the CSI host path driver. Create a very simple app, which is, like in this case, is just a busy box, and create the pod with the raw PVC. Since it's the demonstration, we're actually just going to create a few blocks using DD, right? I just used an odd number of block addresses. just so that we can view a finite amount of data here. So we take a first snapshot. The volume snapshot class is part of the CSI hostpod driver, right? Say it's ready to go. And now we'll view the allocated blocks in the system. So we talked about the CR. So I just choose this point to look at the actual CR which is installed. You notice in the spec section there is an address, there is an audience string, and there's a CA certificate, which were all provided by the CSI driver on installation. Okay, that's critical information. It gives the it's needed by this tool and the backup application to connect to that sidecar. All right, let's continue. All right, so now we're going to actually launch that tool. This launcher, right? It's the I'll show you the YAML a little bit later, right? It runs in a separate pod, and in this case, we've invoked it with the name of that PVC, right? Sorry, the name of the volume snapshot, and the namespace of the volume snapshot. This one, it's telling us there are 5 blocks. There are 5 blocks, and these are the byte offsets of the blocks. The 5 blocks present, and these are the allocated blocks of the volume, just as we expect. So moving on, let's modify the volume and create a second snapshot. So I just chose to add a couple of even numbered blocks and changed one of the odd numbered blocks. So once again, we take a snapshot, wait for it to be ready, and now we can view the change blocks. So the tool is invoked in pretty much similar manner, except that this time we have 2 snapshots specified, the new snapshot and the previous snapshot. And as you can see, it's showing us the changes only. The last one, it doesn't tell you that, it just tells you what has changed between these two. It doesn't give you any history which one came first or the others, just the way this is. So moving on, just to confirm, right, we view the allocated blocks again because we have grown the volume slightly. So we run the same command just with the single snapshot, and you'll see it's got 7 blocks as we've defined. All right. So a little segue into this tool and the code base. So this is the Kubernetes external snapshot metadata repo. So there is the examples subdirectory there in which you'll find the snapshot metadata lister tool. And this one, so this tool uses this iterator function. It also has the pod YAML, which for what we just launched for that CSI client. The YAML takes, when you first run it, the YAML takes a little bit of time to start because it actually extracts the whole tool out there and builds it in your cluster and then copies the data. And that's done in an init container, and then it's ready to go with the compile tool waiting for you. So if we look at the code, right, it uses this iterator package, which we provided in this repo, and it's called get snapshot metadata is the entry point, and if you look at the tool, it's mainly driven by the arguments in the data structure. So, we have arguments for the API clients, the emitter callbacks, right, namespaces, the snapshot names, previous snapshot name, and there are other things which are not going to go in the demo, including things like what's the starting offset. Say your backup failed in some period of time and you want to restart, if you knew where you were, if you've done some checkpointing, you could skip things again and restart from some particular point. So there are a lot of options out there which are kind of useful for backup vendors. The data is actually returned through a callback interface called the emitter interface over here. And we'll see that. The iterator itself will handle every aspect of that workflow. So, they really don't have to mess with anything other than create your CSI clients. Ultimately, the iterator calls these 2 functions, get allocated blocks or get change blocks. I mean, basically that's the 2 choices you have when you create the iterator. You specify 1 snapshot or specify 2. Okay. I think that, okay, that's the end of this. Let's go back to this. Okay.
All right, we got to see the code. So, these slides have already been uploaded to Sched. You can just download them right now because you can take pictures, but I want you to just download the PDF and start clicking on these things. Go directly to the primary resources, go directly to the repo, and then, quite frankly, if you're done with the code, then it's time to talk to management or other influencers or your other peer engineers to help implement and adopt this. We've got a bunch of other times when we've presented these materials, so here's a whole bunch of links, things to send people to read at night and so on. So if you're a backup vendor, please come and join us and we'll help you adopt this thing. If you're a storage vendor, please come adopt this thing and we'll help you. If you are the rest of the Kubernetes community, please talk to your backup vendors, talk to your storage vendors and say, I want my change block tracking. Now, it's really that simple because we are already talking to a number of vendors and projects, but we always need your support in doing so. Not only that, we need your feedback. So please get involved. Come and join us at the Data Protection Working Group. We meet bi-weekly in the morning Pacific time, but if you want to, reach out asynchronously to us in Slack now. We'll respond as quickly as possible, and if you want, we can set up meetings, but it's a friendly group, amazing people. We've already identified a number of the contributors that have already helped out. We want to count you amongst our ranks as well. So thanks for your time. Follow up with us in any way. We'll go on to Q&A now. Please come to the microphone if you have questions.
Yeah, so obviously a lot of vendors already have snapshotting functionality. You're running on Amazon or something like that. Will the Kubernetes snapshots show up as snapshots on the underlying vendor? So in AWS as an EBS snapshot, will you see them in both interfaces, or will they just appear in the Kubernetes world?
If you're talking of Kubernetes snapshots, right, this spec operates on Kubernetes snapshots. It's up to the CSI driver, which created those snapshots, to support the CBT spec. But we actually give them the IDs they have put in the Kubernetes objects. We give them back to the CSI driver.
So
I'm not sure if it answers your question.
So you don't know yet, or you're expecting that they will, or?
At the end of the day, there's still volume snapshots. We don't touch those. All we're doing is doing the difference to show through metadata which blocks have changed effectively. That's all the API effectively does. So same snapshots, same vendors, just a different way to now access and find out which blocks I need to retrieve to get me up to date. Does it make sense, sir?
I think so, thank you.
Okay.
I can add one more thing to that. It's the CSI driver that generates the difference. For example, you mentioned the EBS Direct API. Well, that comes from EBS. So if AWS EBS was going to extend their CSI driver to support this, they would use their API under the covers to source the information. We do not look at the volumes ourselves. The sidecar talks to the CSI driver, which does the efficient thing for its storage. Maybe that's closer to what you're looking for.
And the AWS EBS team has participated in the Data Protection Working Group. They're thinking about this, but please request it, and they will probably advance their agenda faster. Next question, please.
Okay, so this CBT requires CSI driver vendors to open a service, generate some CI certificates. So do you have any materials how to generate them, how to rotate them? Because this is new to CSI driver vendors.
No, we leave that to the CSI driver vendor of how they do it. Every platform seems to have different ways of doing things, right? So we specify what we give a specification. For example, even the RBAC policies we mentioned, we say what has to be set up. We don't provide any YAML to do it. We leave it to the backup app and the CSI driver to do it, because every cluster is managed differently, so we cannot get into that space.
Okay, thanks.
So, currently we are using snapshots for nothing really, because there's so much distrust in having a snapshot. So, like, what exactly are snapshots good for? Like, usually you would use PG backup or MySQL backup for anything relevant, and then there's like the stuff that shouldn't have to have backups to begin with, like badly written applications which store their state in some dubious file thingy.
So there's an excellent white paper. There was a talk just before this which talked about the range of the whole spectrum of backups and what you expect. Volume snapshots, right, give you crash consistency at the lowest level, right? If you want to go higher level to application, I think what Dave, you called it application consistency, then you do something like PG dump or, or generated stuff. There in between, there's quiescing the apps. If your app has multiple volumes, how do you do a group snapshot? There's a whole spectrum of requirements depending on how complex your application is and how sophisticated your backup software is. So this is, addressing the base level, how to be efficient between two snapshots.
At the end of the day, you need primitives on many levels of the stack in order to assure data protection. You need this option no matter what, and the operators hopefully can call down to this if they need it. There are many ways to solve this problem. This is a foundational one that we've needed forever.
Okay.
Thank you, everybody. That's our time.